Hi everyone. Welcome to the Temporal Graph reading group this week. Um, yeah, we are glad to host Kiarash, who will be presenting MiNT, multi-network training for transfer learning on Temporal Graph. This is also a joint collaboration with me and many other researchers from McGill and University of Manitoba and other places as well. And some quick words about Kiarash. So Kiarash has been presenting, I think, for a few times now on this reading group. So Kiarash is currently a PhD student at the University of Manitoba, under the supervision of Dr. Junet Akora, and he has published as a first author in conferences such as NeurIPS, iClear, and ICBC. His research interest covers a wide range of topics, including temporal graph learning, topological data analysis, and blockchain data analysis. Um, so I will hand the mic. So actually, I will start with the motivation. So I'll hand the mic back to myself today. Um, and I will share my screen. One second. So for the first 10 minutes of the talk today, I will talk about a little bit about the motivation for this project and kind of why we started working on this project and its history. So actually we have been working on this project for quite a bit. I think starting from earlier last year, I would say. Um, and it has taken a long process because it's a different way of doing temporal graph learning. So I will explain what I mean as well. So here's the title of the presentation for multi-network transfer benchmark for temporal graph learning. So I will explain what do we mean by multi-network transfer and what we did in the paper. And the code and data set is publicly available. You can find it in the Scaling TGN's repo here. Um, and some quick words on the team, on the project. So Kiarash, Bao, and Razieh are the lead on the project. And then it's also a joint collaboration from me and Farma and Purpak and um, Rehane, Paris, Guillaume, and Junet. Um, so I'll first talk about the background and motivation for this project. So basically, since for a few years, has been like a lot of talk on foundation models, and similarly in the graph field, we have also seen foundation models, and I would say that this year is one of the first years that we see um, kind of good graph foundation models or foundation models that can work in practical scenarios. Um, so on the LLM side, there's many different LLMs nowadays, like Gemini, like GPT, and so on. On the graph side, there's foundation model from Google. There's Kumo RFM. So now we start to kind of see first generation of foundation models that work on relational data. And we all know that the key success of these foundational model is scaling, right? So how do we scale our model to not just narrow focus on a single data set and their behavior? So how do we learn from all available data set? And more importantly, how do we train our models to adapt and learn across data set that is beneficial and transferable? So that's the motivation, kind of the high level. Our goals. So thinking about how do we change our training procedure, how do we change our evaluation procedure, and how do we test the transfer capability of these models. So quick overview of what I discussed 2 weeks ago as well on the benefits of foundation model, right? So uh, so why do we want a foundation model for temporal graph, right? So currently what we have are models that are training from scratch for a single network, requires hyperparameter tuning before you can do any of the inference things, and you keep one set of model weights per data set, and you require domain expertise to understand the hyperparameter, to understand the model, to tune them for the use case. Um, and the benefit of a foundation model is that potentially you can directly inference on data that you have seen or never seen before. You can transfer knowledge where there might be low data. You can adapt across different tasks, and you can also potentially adapt across different modalities as well, right? So I've discussed this slide before on the crossroad on different way of thinking about foundation models on temporal graph. So there's two approaches. So 2 weeks ago, when we look at TG Talker, we are looking at how do we adapt LLM for temporal graph data. So LLMs can provide us with capabilities that doesn't exist before in temporal graph learning. So namely the textual explanations and direct inference capabilities. Because they're already trained, you can just feed data into it and it can um, tell you things about the data. And what's most interesting to me on that front is the explanations generated by these LLMs, which is just impossible to do with any TGNN models because all they can give you are output probabilities. And there might be ways to look at their subgraph and activation, but it's very complicated and very difficult for very non-technical people to do. While with LLMs, you can take your data, feed it, get some explanations. Hopefully, it's plausible, uh, but for the most part, it can give you pretty sensible explanations from what we see, right? And then on the other hand, we have the focus of the talk today is how do we design novel architectures and algorithms for foundation model training? So this talk, the main talk, we're going to focus on how do we construct the data set, how do we test on existing TGNN. So we're not focusing too much on the architecture side, but because we don't really have a foundation model training algorithm for temporal graph. So we take the first two steps. One is having data set, and one is proposing ways to adapt current training regime to work with multi-network training, right? And a similar vein, there's the REL GT paper, which is also a very interesting read. Um, but that one is focusing on the RDL side, right? Um, and yeah, so I'll be presenting multi-network training for temporal graphs, or short for MiNT, right? Um, so in standard temporal graph learning, as shown in the visualization here, so you can take something like TGN, you can take something like GCLSTM, so you can take any kind of model. They all essentially do the same thing. Um, and of course, there's some small details on, the data type. You're looking at continuous or discrete, and, their model architecture and so on. But essentially, the idea is the same. You will take a training set, you will have some test set, and you train and test, usually in chronological order, on a single temporal graph, a single network, right? So you take your model, you train it from scratch, you then test on this network, right? So this makes a lot of sense if you have a specific application, you really want to get the best performance possible using all your weights on this network. However, that's usually very difficult to achieve because this requires a lot of manual hyperparameter tuning, requires high level of understanding of the task that you want to do, what is useful, what is not useful, which architecture to use. You need to make a lot of design choices when you actually want to apply this in practice, right? So the machine learning question is, so in the standard temporal graph, when we given an observed history of a network, can we predict the future on the same network? That's kind of the core of the question of the field of temporal graph learning, right? And then, so the question that we're asking in this work and in general, in high level, is can we learn from multiple networks, right? So, so in practice, think about you have different transaction networks, you have different cryptocurrency networks. These have different interactions across all these networks happening in real time every day, right? So you could have one transaction network in USD, one transaction network in Euro, for example, right? And these might be from two different institutions, two different banks, for example, right? But many of the patterns and things that are underlying these transaction networks could actually be learned and shared by the model, right? Do we really need a model to be retrained on scratch for every single use case? And we are also limited by whatever data is only available for this specific data set, right? But if we can leverage the power of all the available data set, all the available network, then we can not only predict for the network that we want to, but also for networks that we haven't observed or networks that happens in the future. Because here we are learning basically a a forecasting task, right? So we are learning how things are gonna repeat and change and become in the future. So that's kind of the core idea. So the test set here is that we want to test on a chunk of data that we haven't observed, which will be a chronological split on the network that happens in the future, right? Um, And however, there's multiple challenges here. So I'm going to slightly go back and forth among the slides to show you what I mean. So basically, the first one is the current training only tells us we need to loop for training, validation, and test, and we are done, right? But it doesn't tell us how do we train on two networks, right? Do we loop over their training set altogether? Do we loop over them individually? How do we reset time, right? Because one network is happening in chronological order, the other one, we need to restart from the beginning of time, right? How do we do these kind of things? And we also have a lack of data sets. So even with TGB, there is very little temporal networks in terms of what you need to study scaling, right? There's less than 20 data sets, which is not enough. And they are very disjoint and very different, right? Um, and some of the other challenges that I will show in the illustration, right? So one thing is you want to learn across multiple networks. Okay, sounds good. But some of the network might be born much later on than some other networks. So for example, let's just say in the illustration here, the transaction network for the Euro one is starting in January, while the transaction network for USD is starting in May. So how do you learn across different time span? Because now we are talking about different networks, right? And also they have different set of nodes, right? So we cannot assume that two networks will have the same set of nodes. It's almost never true. So how do we adapt to different set of nodes at these networks while still having the same model? Can we transfer something there, right? And then also there's things about, yeah, completely unsynced network. So what if my test set, so let's say starting in August 2025, now contains suddenly a new network with a different set of nodes and different set of edges. Can we directly transfer what we learned here from the history until July into this new network from August, right? So there's many of these questions and are very interesting to explore and understand. How do we design architectures? How do we design algorithms to perform these type of learning? Um, and yeah, so we will start talking about this paper, right? So going back to what we see before, so there's two main research questions. So the first one is, can we have temporal graph learning models? So in this work, we take existing models. So can we have existing temporal graph learning models benefit from learning across multiple networks? So what I want to highlight here is that we should not think about it as a graph learning task. So when I started the project, I was thinking about this is similar to molecule foundation models, where you see a bunch of molecules, they kind of are distributed like so let's say you have different 4 million different molecules, and they are individual graphs. So um, so the correct way of thinking about this, I think, is that we actually have multiple time series because temporal graphs are chronological first. Without timestamps, nothing is ordered in temporal graph. So timestamps are the most key feature that we have on the graph, right? So we're actually doing a kind of multi-time series learning problem, except that we actually have graph data attached to the time series. So that forms the temporal graph. So from that perspective, I, um, I think the answer is that we can benefit from learning across multiple networks or more in general, multiple time series because there are patterns and evolutions in the time series or the changing of the data that we can transfer across networks. So we also see that in the empirical results, which Kiarash will go through in detail later on, right? And then these networks can have different behavior and patterns, but some of it will be shared and can be learned by the model. And the second thing is, can we generalize to previously unseen networks? So this also brand new in literature in the sense that how do we take a trained TGNN and apply it to a network that you never see before, right? So this means that you need to reset your node embeddings. You need to reset and update the set of node space that you are working with, right? And here the idea is that we have a lot of data until today. Can we leverage that data to test on things that starts tomorrow, for example, right? So in this work, we'll partially answer that question as well. Yeah, and then I think yeah, I think I will hand off here, right? Kiarash, you want to take over?
Yes, thank you, Andy, for the great opening. So let me share my screen. Uh, can you see my screen? Double check that.
Yeah.
Yes.
So thank you, Andy, for the presentation. So yeah, now we know the problem and the challenges that we have here in this area of research. I'm going to go through, first of all, to the contributions that we did to tackle the problem that Andy mentioned, and then go over every single one of them step by step and explain like the details on that. So in MiNT, for the first time, we did four new contributions. Like the first is, as Andy mentioned, in the current temporal datasets, we don't have that much diverse datasets. So the biggest one is 20, and if you want to do the transfer learning and train with the different temporal networks, you basically don't have the enough number of diverse and big networks. So the first contribution here for us is to introduce a new large data set, 92 temporal data sets, and the time spent is almost 6 years of data in each of them. I will go shortly for some details on that. So first of all, we introduced this data set in two different domains, financial and social. The first contribution is now we have like all these data sets, 92 data sets. How should we train a temporal GNN on that? Because these data sets are completely diverse. They have a different starting time, end time, and they have their own transaction behaviors, or even in social networks, they have different semantics on these data sets. So how should we want to train? And we introduced the MiNT trained algorithm. This is the next contribution. For first time, we studied the scaling trend and the sign of scaling on temporal graph learning. And we also observed the zero-shot transferability of a model that trained on multiple networks and apply that to the network, to the unseen networks without any training. And we did this within and across domains. So let's get to each of them step by step. So first, the MiNT dataset. To tackle the challenges of not having large enough datasets, we extracted 84 distinct transaction networks from ERC20 Ethereum. So the time span is from 2017 to 2023, so almost 6 years of data. This is a big data set. Each of these transaction networks, they have their own investors, they have their own transaction patterns. These are distinct transaction networks, like the example that Andy mentioned, like dollar and euro, like USD and euro. So these are pretty same. And noting that we have hundreds, thousands of these token networks, like people creating tokens every day, and they are in the market. People are investing on them, and this is a very dynamic platform for tokens. So we extracted 84 distinct ERC networks, 3 million nodes, 19 million edges, very big networks, and then we discretize them because we want to study this problem in DG setting. So we create 7 days weekly snapshots out of that, and then now we have this data set, like all of this data set with snapshots and ready for going for the next step. Before that, let's briefly look at MiNT dataset characteristics. So we have 84 networks. All of most networks, we have more than 10K nodes and over 100,000 edges in each of these datasets. Our lifespan varies from 107 days to 6 years. And for every single network, we make sure that we have at least one transaction each day. And another metric that we evaluated on our datasets is novelty, which shows the portion of newly edges coming to each snapshot. So this number is more than 0.3, which shows like the highly dynamic nature of our dataset. People are coming to these networks, doing transaction, going out. So we see lots of new edges and new nodes in this transaction, datasets. After like creating all of these 84 datasets, we split this dataset domain to 2 splits, like train splits and test splits. So train splits, we use this for just training the models, and test splits is just a holdout dataset. We don't train anything on them. We just test our models on that. Comparing these two, I want to show that we have a diverse set of edges. Notice the different networks, they have different behaviors and lifespan. So it's diverse enough to study the transferability on these networks. To show the inductive dynamic nature of our dataset, we did another also experiment to show the node overlaps. So node overlaps in these transaction networks, nodes are the investors, the people that coming to the network do transactions, transferring money from one account to another account. So these are the nodes that we have like in this transaction networks. And to show like these datasets are completely dynamic to study this transfer learning, we did 2 more experiments on these nodes. So first, we evaluated the node overlap from train versus test datasets. So we have 64 train datasets and 20 test datasets. These are the datasets that we have in tests, so like 20 transaction networks in holdout set. We just compare like the nodes that we have in every single one of them with all the 64 networks that we used for training. And we observed like only 2% of nodes are overlap. So it means we have just 2% of addresses and people that they are investing in all of these test networks on average. And we also did another experiment, like each of these token networks separately in test dataset, they have train and test splits. So we use the first 70% of a snapshot for training, 15% for validation, and the last 15% for test. So we also did the node overlap experiments from on test and train split on each of these networks, and this shows only 4% of node overlap. Again, this proves we have lots of new investors coming to the network and going out. So the networks are very dynamic and inductive. The next step for our dataset is adding like another domain, because if we just study one financial domains, it's not, it's not completely enough to show the transferability of this MiNT. So we added another domain, the social domain, just on top of our financial that we had before. So we added 8 temporal social networks in different applications that you can see here. So these networks are varying in sizes, interaction types, and they have temporal patterns. And each of them, the edges in them, they have different semantics. So 4 of them are QA platforms, some of them are email lists. So these edges are different in terms of the semantics behind them. And we also split them to 2 sets, 6 for training and 2 for holdouts, same as what we did for transaction networks. And this is the MiNT dataset. So at the end of the quick conclusion and why we use this MiNT, because now we have a very large temporal graph benchmark. And this is larger than all of the datasets in temporal graph learning that we have today. with 92 networks, and 84 of them, we newly introduced them to the research community. And these are large enough, inductive, dynamic, and they have different sizes, different durations, starting times. So they are different and diverse enough to start studying about this problem, transferability. We have new edges, new nodes, and we have both financial domains and social media domains. So we have also two domains that we can start studying this problem on that. And it's a very good fit for scaling trends like what we have in NLP and CV because the large and various number of data sets here. So this was the MiNT dataset. And now we have the MiNT dataset, like this diverse dataset that we can start studying this problem. We need a task on that. So we have all of these graphs. Let's define a good task on that to study this problem and see if we can do any transferability on that. So in MiNT, we do discrete time dynamics graph. So we go with DTDG. And in this DTDG, we have different set of graphs and different snapshots. So each graph, we split it to different snapshots. And here we go with weekly because it completely fit with the nature of transaction networks that we have. These transaction networks, the transaction take place like in timestamp blocks. And weekly is good in a sense that people do like transaction weekly patterns and these sort of things like in the network. It's somehow weekly. So weekly snapshots are a very good fit for transaction networks. So in DTDG, you get the graphs, and these graphs in our case are different data set that we have, and in each of them we have a snapshot. So we have the observation part of each data set. We look at all of these snapshots and we want to predict something for the next time step that we have. Let's say we look at this week and we want to predict something for the next week. And what we predict here and what is our task is graph property prediction, which is another novel task that people are studying in this area of research. And in property prediction, what we do is we look at the observation split of the network. And for the test snapshot, we want to predict some property of this graph. This can be gross or shrinking number of nodes, density, and like different properties of this graph. And this task is very important in many domains, like in financial domains that we are doing this MiNT on that. It's pretty important to predict like the growth or shrink of edges. And it shows like if this network will be successful like in the future. And is it good to invest money on that or not? And in social networks also it will show like the changes that you will see in the future. We define two different tasks for MiNT to be evaluated in the next step. So first is network growth or shrink, and growth or shrink here is the number of edges. And how we define this task is we get the current snapshot and we compare the number of transactions in this current snapshot that it's in our observation period with the next snapshot. And if we see any growth in number of edges, we put label 1, which is a binary classification. And if we see any shrink in the number of edges, the label will be 0. So it shows a decreasing trend in number of transactions here. So this is the first task. It's pretty important and influential in financial networks. It shows like the activity and engagement on the network. So it's a kind of indicator. If you see like a growth in the network, it's pretty good for doing some investment and active. People are coming to the network, putting some money on this network. So it's very important. You can take some strategic and financial decisions. It's pretty good for risk management decision based on the network health. And also you can do some operational and resource planning if you own any platform related to these networks. This is a very important task. And to also evaluate our model on another task to show like the promises that we have here on another task, not just limited to one task. We also introducing another task called largest connected component, or LLC growth or shrink. And this is the number of largest connected component in the graph. Again, growth or shrink. So if we see more LLC in the network, like in the future snapshot, the label will be 1, and if it's less than that, so the label will be 0. So it's a binary classification again, and it's the gross or shrink of this LLC. This is also an important task because it shows you like the cohesion signals in your market. So if you see like more LLC show it's like interaction between participants are solid, and like the fragmentation of network is less than before. So it's pretty important, and it shows like the efficiency of your network. And again, it's good for forecasting like the health and some risk management decisions in your network. So these are the two tasks. These are two tasks that we will use in our evaluation process and empirical studies that I will share shortly, like in the future. Now we have some understanding of the data set that we introduced and also the way that we want to tackle that. Let's go to the MiNT methodology. And this is our training methodology. Now we have like all this data set, how we want to train like a model to on all of these networks and then inference on unseen networks. So the goal is here to train a temporal graph model on all of these different networks and then do a zero-shot inference on unseen network. And during the inference, we don't want to do any kind of fine-tuning or any kind of training or anything on the model. So the weights are completely frozen. We have 3 steps in this MiNT algorithm. So first is our data split, then is our training process, and the third step is our inference. For the first step, it's our data split. So we get all of the data set that we have. Again, the training split that we have 64 networks here, and the whole data split that we have 20 unseen network here. Then for this 64 network, we split them randomly to some overlapping sets. So we get 2, 4, 8, 16, 32, all the way to 64 networks. So these are different set of networks that we use for training in the next step. So let's say in split 4, we have 4 of token networks. In 64, we have 64 of networks. And when we go from 2 to 4, we keep this 2, we add 2 more transaction networks to that. Then if we go from 4 to 8, we keep this 4 and we put 4 more data sets on top of that. And then we train all this model independently on these training networks. In the next step, which is our training process, we get every single pack of these networks from 2 to 64, and we start training a model on that. And in each epoch that we have, we do 3 steps. First is our order shuffling, then it's context switching, and then the final step is our TGNN training, which I will explain every single one of them like in detail. It's very important because we want to capture the shared temporal patterns across all of these networks. So we believe we have some shared patterns across all of these networks, and we want to capture all of these things. And we don't want to overfit to one single graphs. And it's very important to know that we have lots of different tokens. They are coming to the market every day. So let's say thousands of them. And it's not feasible to start training a model for every single one of them. And even you don't have enough data. So you get like this new token today, and you have just less than a week of transaction, or maybe less than a month or something. And you want to predict the future trend of this network. So the data that you have currently is not even enough to train one network from scratch. So this is the very big challenge here. And then after this training, we want to do a transfer to unseen temporal networks. Now let's get to every training epoch that we have in this training step. So first of all, like this is the TGNN training. So for TGNN training, any discrete time temporal graph can be used here. So we used HTGN and GCLSTM, but you can basically put anything you want. And this should be just a discrete time temporal graph. And it will be trained like during this training step with our additional add-ons on top of that. So the first thing that we do before training this TGNN is randomizing the order of networks. So we have like different packs. And let's say in 64, we have 64 different networks. And this network should be trained on every single one of them during each epoch. So first thing we do is we randomize the order of the network, and this is good because we prevent them all from learning a fixed order, because there might be some signals in just passing the fixed order of networks to the model, and we don't want to them all to just learn this, because this is not based on, let's say, the real world scenario. And the next is the context switching. So in all of these TGNN networks, we have some historical embedding and kind of memory, and something that keep the context of this network. And to prevent the bias transfer between graph, we do a context switching, and we reset all the historical embedding when we go from one network to the other network. And by doing that, we force them all to adapt to each network unique structure during training that single network. And then going from that network to the other network, there is no historical embedding or anything from the previous network. So these are two important steps that we do during our training process. And then after we train them all, each pack model, we just freeze all the weights and store all of these models. Do we have any question?
Yes,
Yes,
if I can
Victor.
just interrupt, can you go back one slide? Because I have a quick question
Yeah.
on this. So when you're training this HCGN and GCLSTM, are you using your growth shrink metric, or are you using some other loss?
No, this is a lot like end-to-end model training. We are using the task that I introduced, the binary classification task.
All right,
And
cool.
the loss comes from that.
Perfect. Thank you.
Problem. If you have any question, just feel free to interrupt me. I'm okay. So now we train them all. So what we do is we want to assess the performance of each model without any training or fine tuning. So we freeze these models like from MiNT 2 to MiNT 64, and by MiNT, let's say 2 or 64, I mean this model trained on 2 networks, and MiNT 64 trained on 64 networks. So then we get our test networks, which was a pack of 20 networks without any training or anything. And then I do just a forward pass on the observed part of that, which is the first 70% of the snapshot, and then do evaluation on the test split of that network. This is super fast because we don't do any kind of training or anything during the inference. And it's pretty fast for adapting to new completely unseen networks, like when you go to the real world problem. So this was the framework, the MiNT algorithm framework, and now we did a set of experiments, like empirical experiments, to show like the promises and all of the abilities of this MiNT for transferability. So firstly, we trained this MiNT model on network growth or shrink task end-to-end. And also we start training some single models. And this, by single models, we mean that we just train this model on this single network, train network. And we evaluated this on the test split of that network. So these parts of the table, these networks are specifically trained on this network and evaluated on the same test split of that network. We took some state-of-the-art models in this TGNN area, and the task here is network growth or shrink. We trained 2 set of MiNTs, 64, and this 64 use GCLSTM as TGNN, and this one used HTGN as the TGNN. And the results were super interesting. So with training MiNT 64 on completely different 64 networks and testing on these 20 unseen networks without any training, we could get the best average rank performance. And even in some of the networks, like 6 of them, we could beat like the models that are specifically trained on that network. And this shows like this model, this MiNT could capture some generalized patterns out of this network. And when you provide enough data and more data to this model, it can learn some patterns out of that and then generalize to some unseen networks. So the next thing that we did some experiment on was the scaling behavior. So if we put more data here, what's going to happen? So we evaluated MiNT 2, MiNT 4, all the way to MiNT 64. And this is the average AUC performance of this growth or shrink task on all the 20 networks. And we see like a neural scaling trend here. So it shows like more networks, better zero-shot performance. A very straightforward conclusion of this show, I would say, when you provide more networks and more data to these models, so you will get better zero-shot performance. And this is without any training. The diversity and quantity of the pre-training network set is pretty important here. So when you put more diverse networks and more larger networks to training, you get better performance at the end of the day. And this is the first empirical evidence of a scaling behavior in temporal graph learning. The next thing is we also did an ablation study on all the steps that we are doing during the training. So without this order shuffling, transferability performance dropped by 3%, which is very significant in this domain. And if you don't do the context switching, again, somewhere around 4% on average. And this shows like the importance of having this context switching and order shuffling during the training, and the importance of MiNT training algorithm. Another thing that we tried was MiNT social. So now we observe like the effect of this transferability on financial networks. But is it just for financial networks? So this was our question. So if this is just for financial networks, so it's good, but it may not be like a kind of real world problem solving, or maybe it's not enough. We tried another domain, which is social networks. So as I mentioned before, we have 8 real-world social interaction networks, and it's split it again to 6 networks for training and true networks for evaluation. Trained exactly same as before with MiNT algorithm, and these are the results that we have. So the standard TG, the standard HT agent single model has been trained on each of these datasets and evaluated on them specifically for them. And these are our MiNT. Like again, if you look at them, you see same trend in social networks. When you put more data in the training, you see a growing trend, like getting better performance, which is pretty interesting. And in one of them, even Reddit B, with MiNT 6, we could beat the single HTGN trained on this network, which was really interesting. And but the thing is, in these social networks, we have a big challenge. So we don't have that much large data set with all timestamps and good enough to train like a very big model, like what we did with financial networks. So there we had 64 here. We could find like 8 that could fit into our problem. So this is still one of the things that we are investigating, to put more larger social networks to our data set. And another thing here is that these networks are more diverse and heterogeneous, because like in these social networks, like the edges are different, the semantic behind them are different. Nodes are different. In some of dataset, nodes are emails or people, and in some of them these are like questions that people ask like in different platforms. So in financial networks, we know that all of the nodes are investors, and all of the edges are transactions. So it's easier for model to get like this behavior, like the patterns, because everything is somehow similar in sense of like meaning and semantic, but here is not. So we have different meaning and semantic. So this is more challenging, but we again observe the same scaling behavior. The next thing that we tried was MiNT mix. So this is another interesting thing that we wanted to see, like what is the effect of that. If we just mix the domains and do some cross-domain generalization, what will we see? So let's say we train a model with both of these domains. We trained a balanced MiNT with 6 financial networks and 6 social networks all together. Like now we have a training set of 12 networks. And then we tested these networks on all the data set that we had, like 20 from financial and 2 from social networks. And it was awesome. Like the MiNT mix beated, like we got like the best average rank again with training a MiNT model with both domains. So if you see, like, even in some networks, and this MiNT, this is, by the way, the MiNT 12 is just the MiNT that trained on 12 transaction networks. And this MiNT 12 mix is 6 financial networks, 6 social media networks. And in some of the datasets, like even financial networks, adding some social media, social networks to that could improve the results. And that was pretty interesting. If you look at this XCN, like training a model with just 12 financial networks was AUC around 76. And when we replaced 6 of them with social networks, we got even better results. And that was pretty interesting. This was another test that we did. And another task that we had before, so was LLC, largest component, connected component that we have. And this is our additional property task. Again, same training, do zero-shot evaluation after multi-network pre-training. And again, here, same trend and getting the best average rank with MiNT 64 over like the standard HTGM. And same trend here, better zero-shot, more data set you have, larger multi-network pre-training, better zero-shot performance you will get on this task. And again, MiNT 64 achieved best average rank on test networks. And at the end of our experiment, this is also very important to note, like what is the MiNT time complexity? So the thing is, we have a training time and inference time in MiNT. So one time you train them all, and this is the time that you put for training, and we evaluated that this is linear. So when you put more network to training, you get more training time per epoch, which is what we expected. But the very important thing here is in MiNT, you don't need to do any pre-training or fine-tuning during inference. So all you need to do is you just get the model out of the shelf and put it there, and you get your new network, whatever it is. It can be financial network, it can be social media, whatever. And then you want to predict a trend, like growth or shrink in number of edges or LLC or like tasks that you trained before. You don't do anything, basically. You just do a single forward pass to the end of like turning a split or like whatever setting you have, and this is fast. It's in order of less than a minute, and then do your inference and get your final results. And this is pretty interesting, because if you want to start training a model from scratch, you need to train this model like maybe for a couple of minutes, hours, something, if your model is big. But no, you don't need to do that. You just apply on the go and get your results. But this is not the end of the way. So this is just the beginning. So we introduced a new research direction here. It's pretty new. It's the first time that we train TGNN on multi-networks all together. We observed the transferability. We observed the neural scaling behavior, all of that, which if you provide more networks to that, you see a very good trend. It's pretty similar to LLMs. When you provide more texts and more like data to that, you will get better performance at the end of the day for transferability. We want to expand our task and domains. So currently we have just the network growth or shrink and LLC task, which are graph level property predictions, but we can use this for other tasks. So, and also we want to extend this to different domains, both our datasets and our evaluations. This is another future direction. And at the end of the day, the goal is to create a temporal graph foundation model, which is a pretty new research direction, TGNN. So the goal here is to train a model, a temporal graph model on some datasets, and then it can be multiple tasks, it can be multiple domain, or it can be just one task or one domain. And at the end of the day, you just get this model, apply it to whatever you have. Like it can be another domain even or another task, and you get like the prediction out of that. So this is what we want to introduce to the research community. This can be a beginning for this research direction. And yeah, this was a quick overview out of MiNT and what we did. And if you have any question, feel free to ask or send me an email. I'm very happy to engage more on this new research problem. And thank you for your attention.
Yeah, thank you, Kiarash, for the nice presentation. So if you have any questions, feel free to ask here. We still have a few minutes left.
I have some questions. We can definitely go over time, but maybe I can mail them to you later. But I think the first one, if you go back to the baselines that you showed or the models that you compared against, I think we previously in this meeting kind of talked about, you can see this as time series, right? Where you, for each snapshot, have, a graph. Have you evaluated this against
Mhm.
any time series models where you basically collapse
Sorry, I
each graph?
guess
Oh, sorry.
I can't hear you, Victor. I guess your internet
Oh,
connection is not good. Like you're lag.
sorry.
Yeah, you can also type in the chat. Yeah.
Yes, I sent it in the chat. Sorry.
Oh, that's a very good point. We actually have persistent forecast, right, Kiarash?
Yeah. So we have like the persistent forecast in the paper. So task is not that much obvious. So it's a kind of. Let me read the question. Maybe the question is about something. Train a time series.
Yeah, I don't know. I don't know if I'm lagging, but it's basically, collapse the network into a summary statistic and then build a model on that.
Uh, in theory, we can do that, but two very important thing is here we have like a graph, and sometimes we don't have even like enough data for doing that. So we have just a network, and we want to apply like a model on top of that and just get some prediction out of that. This is one important thing. So we have cold start problems in some cases that we don't have even that series to do this kind of modeling on top of that. And also we have like a persistent forecasting a baseline in our paper, which shows like this task is not a kind of obvious task. So because you need to look at the graph, so this problem is like that. So you need to look at this graph, get all the patterns, and then predict the future trend. And this trend is the future trend of the network. So based on the current observation point, like you have this snapshot looking at that and you want to predict the next trend of this. And this is what we are doing here. I'm not sure if I answered the question.
Yes. I also have one more question. If no one else has one, I'll write it in the chat.
So for this embeddings, it's important because it's part of the TGNN. So currently what we do is we do same split, like train validation test. So we do a quick forward pass on what we have right now, but we don't update anything like on the model data or anything. So the model, we don't change anything on top of that, and then we predict based on the forward pass that we did. We didn't evaluate explicitly if we don't do this forward pass on inference, what we will see. But the current setting is just go for, if you want, let's say, to predict T2 and you have T0 and T1, so you can do a forward pass on T1 and T0 and T1 and then predict the T2. So this is what we are doing here.
Cool. Thank you.
Okay. And thank you very much, by the way, for having me here. It was a very interesting presentation.
Yeah, thanks for the presentation, Kiarash. So yeah, so definitely happy to talk about it more if you have more questions. Um, yeah, and thanks for the comments. There's a question on the from the chat. Uh, um, so two questions. One is, how are you preparing for future step? Is it possible to collaborate and any limitations? And then potential future directions. So yeah, sounds interesting. So we can connect. So maybe I think you can reach out to Kiarash to connect offline and can discuss these in more detail. Uh,
Sure.
Also on Slack. So feel free to send messages. And we're at the end of the hour, so we will yeah, we'll wrap up the talk here. And yeah, thanks for joining everyone. And Victor, can you share the recording link like in a bit?
Yes, I will do that.
Yeah. Okay,
Thank you.
perfect.
Thanks for a
Have a good
great
one.
talk. See
Thanks.
you guys.
Bye.